That was an example where we used a balanced chemical equation to find the amount of one reactant required to react with another. Of course, the molar ratios in a balanced equation also tell us something about how much of the product of a chemical reaction we can form too. Like most things in life, though, chemical reactions are rarely 100% efficient. The amount of product that you calculate can be formed via stoichiometry is called the theoretical yield. If you actually perform a reaction and weigh out the product at the end, that represents what's called the actual yield. We can compare the two values to find the percent yield, essentially what percentage of the idealized amount of product was actually obtained. If the theoretical yield of a reaction is 10 grams, for instance, and we manage to recover 10 grams of product, that would be 100% yield. If we only get 5 grams of product out, that would be 50% yield, etc. There's another complication in the calculation of theoretical yield too, the concepts of limiting and excess reactants. It's often the case that reactants in real-life chemical reaction won't be present in completely stoichiometrically equivalent amounts. The limiting reactant is the one that's present in an amount that limits the theoretical yield of the reaction. Any other reactants are said to be excess, and there will still be some of them left over after the reaction is complete. It's always the limiting reactant that determines the extent to which a reaction takes place. Let's look at a conceptually simple example. This is the reaction between ethylene oxide, C2H4O, and water to produce ethylene glycol, C2H6O2, the main ingredient in antifreeze. Whenever chemical companies make ethylene glycol, they use excess water and ethylene oxide as the limiting reactant. This is to make sure that as much of the ethylene oxide, a relatively expensive chemical, is converted into the desired product. Our balanced reaction shows that the reactants combine in a 1-to-1 molar ratio, or 1-to-1 molecular ratio if we visualize things on the microscale. If, say, 3 moles of ethylene oxide react with 5 moles of water, what's going to happen? Only 3 waters are needed to react with all the ethylene oxide, but we have more than 3 waters. Therefore, water is the excess reactant and ethylene oxide is limiting. Since each ethylene oxide produces 1 equivalent of ethylene glycol, we can make 3 ethylene glycols by the time the reaction is over. We used up 3 of the waters, but we started with 5, so we still have 2 of those left over. Here's another example of when it's important to use one of the reactants in excess and have the other one be limiting, making soap. This is a fun activity you can try at home without too much specialized equipment, and you get a usable product out at the end. Glossing over some details, soap is produced when a source of fat, like vegetable oils or animal fat, for instance, reacts with sodium hydroxide. You always want the fat source to be present in excess and the sodium hydroxide to be limiting. In this case, any leftover sodium hydroxide would be damaging to skin when you try to use the soap. By the way, if you're wondering why the soap in this picture looks like crap, it's because I made it myself during quarantine. Anyway, more limiting reactant stuff. Here we're looking at the reaction used to remove excess moisture from the atmosphere in space vehicles. Here, lithium oxide reacts with water vapor in a 1-to-1 molar ratio, forming 2 equivalents of lithium hydroxide. If, say, we have 80.0 grams of water vapor and 65.0 grams of lithium oxide, can we say which one is limiting? And once we determine the excess reactant, how much of that will be left over after the reaction is complete? Finally, how much lithium hydroxide is produced? Let's take this one step at a time. First, we'll determine the limiting reactant, because that determines the extent of the reaction, and hence everything else about this question. For this, try to answer these 2 questions. How many moles of water can theoretically react with our 65.0 grams of lithium oxide? And how many moles of water do we actually have? Remember, there's 80.0 grams of water. Go ahead and pause the video and try these on your own. First, the number of moles of water needed to consume all the lithium oxide. First, convert the mass of lithium oxide into moles using its molar mass. Next, use the 1-to-1 molar ratio from the balanced equation to find out how many moles of water this will react with. This number should be 2.17 moles of water. Next, we'll compare this to how much water we actually have. We take our 80.0 grams and use the molar mass of water to convert it to moles. We get 4.44 moles of water. Now let's interpret this result. We have more water present than we need to react with all of the lithium oxide, so water is the excess reactant. Lithium oxide is our limiting reactant, so now we know it's going to determine to what extent the reaction takes place. All the steps of these conversions are analogous to how we worked out the reaction between chlorine and sodium hydroxide on slides 12 through 13, so go back to that stage of the video if you need a recap. So if water is present in excess, how much of it is left after the reaction is done? These types of questions tend to confuse people a little bit, But really it's not that complicated, at least not more so than anything else up to this point. Try to figure this out on your own, pause the video, and restart when you're done. Let's start by figuring out how much water is consumed. That's the same as the amount needed to react with all of our limiting reactant, lithium oxide. We determined this on the previous slide, 2.17 moles. Using the molar mass, we can see that this is equivalent to 39.1 grams of water. So if we used up 39.1 grams of water, and we started with 80.0 grams as stated in the problem, how much is left? It's not a trick question, just subtract the two amounts, so we get 40.9 grams of water left over. Finally, how much lithium hydroxide is produced in this process? Again, try this yourself by pausing the video and come back when you're done. A couple of slides ago, we found out we had 2.17 moles of lithium oxide, our limiting reactant. Since it's limiting, it determines our theoretical yield. We can see that each mole of lithium oxide yields 2 moles of lithium hydroxide, so the first step is to multiply by this 2-to-1 conversion factor. Finally, we multiply the resulting number of moles of lithium hydroxide by its molar mass to find the equivalent mass in grams, and we get 104 grams of lithium hydroxide. Now let's look at another application of stoichiometry, percent composition and empirical formula. All chemical compounds, you may recall from Chapter 2, consist of specific mass ratios of their constituent elements. The example we used in introducing this was water, which was about 89% oxygen and 11% hydrogen by mass. These are called percent composition, the mass percentage of each element in the compound. If we're analyzing an unknown chemical substance and want to determine its chemical formula, we can use these mass ratios to find what's called the empirical formula, which is the chemical formula of the compound in the simplest possible whole number ratio. For a lot of covalent compounds, the molecular formula, which tells us the number of atoms of each element in the molecules of the compound, is not the same as the empirical formula. We'll need to account for this in analyzing these problems. Let's consider the case of a colorless liquid that is 84.1% carbon and 15.9% hydrogen by mass. We can use this to determine the empirical formula for the compound, and once we know that, we can use the fact that the molar mass is known to be 114.2 grams per mole to find the actual molecular formula. You can see the strategy for this outlined here. We're going to take the known mass percentages, convert them to moles of each element, and find the molar ratios of the elements. From there, we'll get the subscripts for each element in the chemical formula. We're going to start by assuming we have 100 grams of this liquid. Wait, I can hear you saying, why would we do that? Where did that number come from? Good question, I'm glad you asked. Mass percentages are intensive properties, independent of the amount of the sample. Therefore, we could start by assuming that we have any amount of the compound that we want. It makes the most sense, though, to use 100 grams. That's because any percentage of 100 is just the number itself. So we can take that 84.1% carbon and instantly transform it into the same number of grams of carbon. Converting it to moles by using the element's atomic mass, we find that this corresponds to 7.01 moles of carbon atoms. Similarly, our 15.9% hydrogen becomes the same number of grams, and using atomic mass, we find this to be 15.9 moles of hydrogen atoms. Now we need to find the whole number ratio this corresponds to. We're going to take two molar amounts and construct a gross-looking chemical formula, C7.01H15.9. Now, we're going to find the subscript in the formula at this stage that's smaller than all the others. In this case, that's carbon's 7.01, and we're going to divide every subscript by that number. So 7.01 over 7.01 gives us 1, and 15.9 over 7.01 gives us 2.27. At first, it may not seem like we've done much to fix the formula, which is supposed to consist of only whole numbers. If your answer doesn't look like all whole numbers at this stage, we need to figure out what the whole number ratio in disguise is. 2.27 is awfully close to 2.25, so we can deduce that, minus a small discrepancy due to rounding, we probably need to scale things up by 4 to get whole numbers. Doing this gives us 1 times 4 is 4, and 2.27 times 4 is essentially 9, so we get a formula of C4H9. This is the empirical formula, and we can't do much else unless we have the actual molar mass for our compound. As it turns out, that was provided in the problem, so we take the provided value of 114.2 grams per mole and divide that by the combined atomic weights of the empirical formula. 4 carbons and 9 hydrogens added up should give you 57.0, and we get a scale multiple of 2. So that's the number we need to scale both of our subscripts by. 4 times 2 is 8, 9 times 2 is 18, so our compound is C8H18. This is actually the chemical formula for octane, well known for its role as a component of various fuels, including gasoline. Speaking of compounds consisting of carbon and hydrogen, they are an important class of covalent compounds collectively known as hydrocarbons. One common way of determining the formula of a hydrocarbon is via combustion analysis. All of these compounds burn in the presence of oxygen to produce carbon dioxide and water. By burning a hydrocarbon in excess oxygen gas and weighing the amounts of CO2 and water produced, we can use stoichiometry to calculate the amounts of carbon and hydrogen in the original compound and determine its empirical and chemical formulas.